All right, so again, the reason why we're going over this intro is to make sure that you can model what's happening to the charges during a static electricity event, okay? So let's read our introduction here. Static electricity is does anybody know that word? What do you think it is, Aaron? It's ubiquitous. Ubiquitous means it's everywhere. It's very common. Okay, there's your vocab word for today. Maybe go home and use that tonight. Ubiquitous means it's everywhere. It's very common. So static electricity is a ubiquitous part of everyday life. It's all around us, sometimes funny and obvious, as when it makes your hair stand on end, sometimes hidden and useful, as when harnessed by electronics in your cell phone. The dry winter months, which I wish it was right now, just so we could do our little activities, are a high season for an annoying downside of static electricity. Electric discharges like tiny lightning zaps whenever you touch doorknobs or warm blankets fresh from the clothes dryer. Static electricity comes down to the interactive forces between electrical charges. They're talking about your protons and your electrons, your positives and your negatives. At the atomic scale, negative charges are carried by tiny elementary particles called electrons. So again, we need to know that negative charges are carried by electrons. Most electrons are neatly packed inside the bulk of matter, whether it be a hard and lifeless stone or the soft living tissue of your body. However, many electrons also sit right on the surface of any material. Each different material holds on to these surface electrons with its own different characteristic strength. If two materials rub against each other, electrons can be ripped out of the weaker material and find themselves on the material with the stronger binding force. So all they're telling you is that some materials like wool and plastics are more attracted to electrons than other materials. So in the winter months when we don't have a lot of moisture in the air, you can build up charge on these surfaces. This transfer of electrons, what we know as a spark of static electricity, happens all the time. Infamous examples are children sliding down a playground slide, feet shuffling along a carpet, or someone removing wool gloves in order to shake hands. But we notice its effect more frequently in the dry months of winter, when the air has very low humidity, so there's not a lot of water vapor, water gas in the air. Dry air is an electrical insulator. Okay, remember that means that it can build up charge. Whereas moist air acts like a conductor. It moves charge, so we can't build it up. That's why we can't do our activities right now. This is what happens. In dry air, electrons get trapped on the surface with the stronger binding force. Unlike when the air is moist, they can't find their way to flow back to the surface where they came from. And they can't make the distribution of charges uniform throughout again, so distributed evenly. A static electric spark occurs when an object with a surplus of negative electrons comes close to another object with a less negative charge, and the surplus of electrons is large enough to make the electrons jump. The electrons flow from where they've built up, like on you after walking across a wool rug, to the next thing you contact or touch that doesn't have an excess of electrons, like a doorknob, and you get that shock. When electrons have nowhere to go, the charge builds up on surfaces until it reaches a critical maximum, and then it discharges in the form of a tiny lightning bolt. Give the electrons a place to go, such as your outstretched finger, and you will most certainly feel the zap. All right, so then I want to look at this page, and this is just showing us the structure of the atom. So the part that we're talking about when we're talking about static electricity is these orbiting electrons that can be transferred from one object to another. And this is showing us that like charges repel and opposite charges attract. Okay? That's what this is showing us. So remember, these are our protons. These are our electrons. And they're found in atoms. Okay? So we can watch how these charges interact by doing some static electricity experiments. So then two other things to kind of be familiar with is just an insulator and a conductor. And a lot of you have told me you've talked about this before. So insulators are materials that can build up electrons or keep electrons in place. So they can build up charge. Okay? They can build up charge. And when they do that, they become negative. Okay? So glass will hold on to charge, plastics, rubber like a balloon, wood, different types of fabric, wool, paper. These are all examples of substances that, for example, will have their own set of charges, but then can build up extra charge if something else is rubbed against them. Okay? So that's how I'm going to show a neutral object that was once neutral but became negatively charged because something rubbed up against it. Not a bad idea to kind of draw that, because it's going to help you with your assignment today where you're modeling what's happening with the charges. Conductors are materials that hold on to electrons loosely and they allow electrons to flow. So when the insulator touches the conductor, then the charges will flow to the conductor, and that's when you get that zap. So like when you rub your feet across the carpeting, you pick up extra electrons, you touch a metal door handle, and then zap. Okay, these are some examples of electrical conductors. A lot of them are metals. All right, so what we want to do is we want to observe an example of static electricity. Okay, so what I want to do is just real quickly show you this. Okay, I want you to watch this little kid here. Let's see if we can't. Okay, what kind of slide is this, you guys? It's plastic. What's plastic? An insulator or conductor? It's an insulator. So do you think it builds up charge or no, it'll make it move? It builds up charge. Okay, so I want you to be thinking about what you think the charges might be doing when this happens. I love this. Isn't she cute? Okay, I gotta watch that one more time because there we go. Because it's so darn cute. Okay, so I want you to be thinking about what's going on with this crazy hair. Okay, isn't she cute? She's so adorable. Okay, so I want us to be thinking about what's happening in that static electricity scenario. So let's take a look. And then I just put on here, what is causing this boy's hair to stand on end? Okay. Does anybody have any idea? You know what I'm going to do before I start? Okay, this is how I start all my stuff. Let's think about the fact that everything starts neutral, right? So let's to begin with, let's draw some positive and negatives on the slide. Okay. And sometimes when you're doing models, so you can really follow what's going on, if you have a couple different objects, it's sometimes helpful to use two different colors. And if you don't have those right now, that's fine. I will make sure I give them to you before you start your activity today. So I want to show that the slide started neutral, and I want to show that the child's hair started neutral. So yeah, okay. Okay. So now, what do you think happened? What do you think I should do in order to show what happened? So what is picking up the extra charges, do you think, the electrons? Do you think they're flowing from the slide to the hair or the hair to the slide? Hair to the slide. So why are they going to the slide? Remind me. It's rubbing on it. There's a friction there. And Maggie? Okay, so the slide is an insulator. Let's write that. And so that it's plastic, and so it builds up electrons. And again, this is going to help you with your assignment today. So really, I would try to write that down. Okay? So now what I want to do is I want you to keep in mind that you never add protons, but Well, actually, what I can do is I'll do this because I don't want to confuse you. I got to see if I can find some whiteout. And so you'll have to be careful when you're thinking through. So we don't want to add any protons. Darn it. I don't know that I can find any whiteout here. Nobody has any whiteout on them, do they? Darn you. What?
Sounds like a drug.
Well, no. I wouldn't be asking for it.
Any white out on you?
Okay. All right. I'm sorry. All right. So keep in mind that we're not adding any positive charges because that never happens. And I was going to white out some of my negatives to show them being transferred, but I can't find it. So I'm just going to put some unpaired charges here. So pretend that these were here originally because we never add positives. Okay. And I'm actually going to circle everything that's not paired up. Okay. I'm actually going to circle everything that's not paired up so you can see the charges that I want to focus on. So every time I have something that's not paired, I'm going to circle it. And this is just how I do my diagram. So now I want to show that the electrons that used to be on the hair are transferred to the slide. So I'm going to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's make it even. So I'm going to do 12, and it's okay if you don't do the same number as me. We're all going to have different types of models. But I'm going to take 12 electrons that were once on the hair, and I'm going to move them to the slide. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I want to have some consistency, and I want to make sure, I'm going to back my camera up here. I want to make sure that however many electrons I took off the hair, I'm going to put on the slide. So what's the overall charge on the slide? Is it negative or positive? Negative. It's negative. So slide equals negative charge. Okay. And what about the hair? What's the hair got? Hair has a positive charge. So why does the hair stand on end? Does anybody have any ideas? Why would that hair stand on end? What do you think, Lakin?
They're opposites.
They're opposites, okay.
And then they repel each other.
Okay, so they're attracting each other, so the hair is attracted to the slide. Is that what you're saying or no? Okay.
Repel each other.
Oh, the hair strands repel each other. Why do the hair strands repel each other? Okay, so this hair strand is repelling that hair strand because they're both positive and like repel. Okay, and then do you think that the hair strands are also attracted to the slide? What's the charge on the hair? Kaden, what's the charge on the hair? Positive. What's the charge on the slide? Negative. Do opposites attract? So we probably got two things going on here that's making the hair stand on end. We've got hair strands. Okay, so we want to say this positive, and we're going to put like repel. So like charges repel. That's part of the reason that the hair stands on end. Another reason probably is that hair positive slide negative, and so those two things are going to attract each other. Okay, so there's probably a couple different factors that are causing the hair to stand on end. The hair is attracted to the slide, so it's going to kind of pull away from the person and pull towards the slide, but they're also repelling each other, okay, because they're like charges. So I really want you to do some of this kind of thinking when you do your assignment today, okay? So I'm going to